So for hypothesis testing, let's take a look at this example. I want to go back first to this explanation and these assumptions, a couple just simple ones. Basically that your sample size is large enough, because this is for large sample. So n is greater than or equal to 30, and it's a random sample. So, and random sampling, which I have mentioned before, that is not always easy to do, but you make the assumption anyway. Okay. Let's take a look at this example. Let's read it first. Suppose a widget maker wants to make sure a product is being produced efficiently. For efficiency, the manufacturer needs to produce 511 widgets per day. To confirm this, records were pulled over the last 2 months, and I just estimated, say, 36. So they had a holiday in there. The standard deviation, the sample standard deviation was 6, was calculated. The sample mean was calculated to be 509. Should the widget maker be concerned? So that's maybe how it would be asked. Okay, so you want to state the null hypothesis and the alternate hypothesis. H naught versus HA. And this would be stated. So we're going to use, we'll go ahead and calculate the p-value, but we'll use an alpha level of 0.05. Okay, so use alpha to be 0.05, and that's pretty typical for this sort of thing. Is it, okay, so now you got to think through it. Is it a two-tailed or one-tailed test? So you can't assume that they need to make more. That's part of it. Maybe they're using certain energy or chemicals to produce them. So if you can go, say, faster, but that would be less efficient. So you can't necessarily assume a higher number is better. So another, research team came in, some mathematicians and stuff, and said that this, with all the data they had, that 511 is the optimum amount per day to be efficient. So making more wouldn't necessarily be better in this case. So you want to see that it differs from it. So this would be a one-tailed or two-tailed. And you were right. This is a two-tailed test. So two or one-tailed. And then I wanted to write this down too. That's 5%. Okay, so this is a two-tailed test, because you want to see if it differs from that, because that is said to be the efficient. You don't make the assumption more is better, unless it specifically says that. Then your HA, your alternate hypothesis, mu naught. Let's back up. Let's do let's do your null first. Your null hypothesis, H naught, is that mu naught is equal to 511, because that's the most efficient number. And your HA, your alternate hypothesis, is that it is not. That your mu, your actual mu, differs from mu naught. Or, in our case, mu does not equal 511, statistically speaking, right? Because it's always going to be plus or minus on either end. Okay, So we're given all this information. We're given N, S, and all that. So no need to recopy it this time. It's all there. So let's do our test statistic. Z is equal to, always write down the formula if you're using the formula, x bar minus mu naught divided by S over square root of N. That's equal to 509 minus 511 divided by S, which is 6 over the square root of 36. So that's negative 2 over square root of 36 is 6. 6 over 6 is 1. So this is equal to negative 2. So basically, the test statistic is negative 2 standard deviations to the left, or 2 standard deviations to the left. That's what negative 2 means. Okay, so 2 standard deviations left. So is that in the interval? So let's take a look at that. So your test, your significance level, alpha, is 0.05. And so you're going to be looking at alpha over 2 in these cases. Alpha over 2. So we want to look at that. Alpha over 2 is 0.025. So you say this is Z sub 0.025, and this one is negative Z sub 0.025. So we want to know that actual number, and you can look it up in the chart, calculate it, or they actually have a little table for this. Okay, so let's take a look at the chart. So what's that Z value? So if you go to the chart, you can calculate it, but it's actually right here. We have a two-tailed test. So significance level, 0.05, we use plus or minus negative 1.96. So how you do that, actually, is you go to the table and you find 0.025. I've already highlighted it. Here's your 0.025 exactly, and it's negative 1.96. And remember, you're using the negatives because that's summed from the left. It's this stuff. You can't look over here because it's the whole thing added up. So we know that this side, because it's symmetric, will be the same value but positive. But you can just look those up. This is what you would use. So if you had needed to know, write stuff down, a little note card or something, those are what you would write down. Okay, so let's go back. And so those values are, this would be positive 1.96. This would be negative 1.96. So those are that's what you just calculated. See, it's the same Z. So this is negative 2. So where is it? Is it in the rejection region or not? So here's 0, so it's right there. It is just barely in the rejection region. So this is your Z. That's your calculated test statistic right here. Therefore, what do you say? What's your conclusion? All right, I have some stuff to write down for you. So to that, so thus, the calculated Z value lies in the rejection region, even though it's really an interval on the left. Therefore, what do you say? Therefore, we reject H naught. We reject the null and conclude the widget are not being made efficiently, and conclude the widgets are not being made efficiently. And specifically, that's at a 5% significance level. So if you actually move that further to a 0.01%, what would you get? So if you moved it to a 0.01, then you'd have plus or minus 2.575. Well, then it would be on the other side. So if we used, so this is an aside. If we used alpha 0.01, we would not reject H naught because the Z value for that 0.01 two-tailed would be over here. Whatever I said, negative 2.757. Let's look it up again. 2.575. Even if it was left-tailed, if we're just looking at left-tailed, you would not reject either because it's negative 2.33. Okay, so you can see it depends on the significance level. Now, let's calculate the p-value. That's the probability that Z is less than negative 2, right? It's the actual, we're using the actual calculated test statistic. And then you're adding the probability that Z is greater than negative 2, positive 2. So it's going on either side. And you add those up, that's going to be, so if you look up negative 2, so here's negative 2, it is 0.0228. And then the right hand side will be the same because it's just, they're symmetric. It's the other side. So if you go back to here, that probability is 0.0228 plus, and then that would be the same, 0.0228. And then you add those up, calculator, and you're going to get 0.0456, which is less than 0.05, which equals your alpha. And so if your p-value is less than your significance level, then you reject. Write this definition down. If the p-value is less than or equal to the given alpha level, then the null hypothesis, H naught, is rejected. I guess I didn't write that down. Then we reject the null hypothesis H naught. Then we reject, okay, the results, and then you can say after that, the results are statistically significant. And you always want to ask at what level when people say it's statistically significant, but what level did they choose? So you want to know that. So they could have chosen like 10%, and then it'd be a lot different. So if you increase this, as we showed above, to 1%, then you would not reject. You would not be in the rejection region, and your p-value would be this. Let's see. Yeah, this value would be greater than your 0.01, and you would not reject. Okay, so let's look at some more definitions. Type 1 error and type 2 error. Errors in statistical tests. Okay, so type 1 error is reject the null hypothesis when it is true. Okay, so that's when you reject the null when it is true. So maybe you, well, it could, it wasn't random or something, something else occurred. They talk about probability. Probability, that is alpha, which is that region, basically. Type 2 error is you fail to reject H naught when it is not true. So fail to reject the null hypothesis, the null H naught when it is false. And they talk about the probability of that. We're not going to get into it. Is beta. And there's some details after the main concept we're not going to get into. Let's take a look at this example. Another one. This one's 9.13 from Mendenhall. Let me zoom in a little bit so we can read it better. Potency of antibiotic. You can see it doesn't really matter what it's about. It's just you got to figure out the numbers. So, drug manufacturer claimed that the mean potency of one of its antibiotics was 80%. A random sample of 100 capsules were tested and produced a sample mean of 79.7%. With a standard deviation of 0.8%. So be careful with those decimals. You're going to have to move that 2 to the left and to get your right decimal. Do the data present sufficient evidence to refute the manufacturer's claim? Let alpha be 0.05. And I put this in here as well for later, and we'll calculate the p-value. At least we'll talk about it. Okay, state delta. So then we got to do the test. So these ABCs, really, it's always, you got to go through the test, make a conclusion, that kind of thing. Okay, so let's write down our information we know. Okay, it's all there, but let's go back to my notes. So just keep rolling. So let's write down the different information. So our null hypothesis is that mu naught is equal to, and it would be 80%. So you never use percentages, right? So you got to change that to 0.8. So it's 0.8. And your HA, and you always got to think about tails now. Is it a one-tail test or two-tail test? Basically, in this case, the higher potency, really the better. You're claiming it's at least 80. So is it higher than that? Is it at least that? So your alternate hypothesis, you're claiming, let's see, let's write it down like this. So let's go back. I like to write our information first that's given. So what's given is that your claim for the mean is 80%. And then now let's calculate the 0.8. And then we're also given in your sample size, it's 100. When you do the root of that, it makes it easy. What else? Okay, your X bar is given to be 79.7%. Move the decimal, 0.797. And your standard deviation is 0.8%, which is 0.00812. Move the decimal 12. And then they want the alpha level to be 0.05, but we're going to test at 0.01 and 0.001 and just consider the alpha levels, and we will calculate the p-value. Okay, which isn't asked here, but I always like to calculate p-value. So let's write down our null hypothesis. We'll write out some words this time. The mean potency of the population is 80%. Mu naught is equal to 80%. 0.8, which we'll convert to. The alternate hypothesis, the mean potency of the population is less than 80%. Basically, not up to snuff, not good enough. So how do you write that? You would say mu is actually less than mu naught. And you can write in the actual number there. It's fine. So mu is less than 80%, or mu is less than 0.8. So probably write this directly right out of the bat, right out of the gate. Okay, so I left this here because it is a left-tailed test. So this is a left-tailed test. Okay, so those are the things that I went through pretty quickly, but you got to think about that and figure that out. There's a number of examples with solutions posted to go through to get more practice with that. To calculate the test statistics, Z, every time you use a formula, write down the formula. So it's X bar minus mu naught divided by S over root N. Okay, now we write down our numbers. Our numbers here, 0.8, etc. Okay, so it's 0.797 minus 0.8 divided by 0.008 over square root of 100. I wrote out some of the calculation. That's negative 0.003 over, and it's going to be negative, so we know it's less than. We just don't know if it's statistically significant or not. And it's 0.008 over 10. So it's negative 0.003 over 0.0008. And then when you divide that, you get negative 3.75. All right, right there. What does that tell you? Well, without even looking at the values of z sub alpha on a left-tailed test, it's way over here. So we this is this 3.3 standard deviations from the mean. Automatically, you're going to reject. It's too far out there. So now you actually look at it and figure out where it is. So let me move this back up here so I can write it in better. All right, so you're at z 0.05 and it's negative. And go back to our table. You could look it up here if you wanted. It's negative 2.575. So you can interpolate. Negative 2.57 is just in between those. So it's right there. And what do they say down here, actually? Oh, they do. They actually interpolate, see? No, sorry. 0.05. I must have done that wrong. Oh, that's 0.05. Never mind. Where's my 0.5? It's right here. There we go. The negative 1.645. Negative 1.645. So there you go. So left-tailed. So you can just use any of these values. Just showing you how you get them. So it's that one. Okay, so go back. Make sure these are those are my notes. Go back to the right one. That one's it. Okay. All right. So this is negative 1.645, but you can do all the calculations if you want. 0.01, that's negative 2.325. 0.001 is negative 3.09. So it's getting closer, but this is still way into the rejection region. So basically, rejected on all levels. Let's calculate the probability. Probability, just to show, I'm actually not going to calculate it. You'll see what I mean. Is less than negative 3.75. So what's the probability that will occur? Well, it's approximately 0. Again, if you go back to the tables, we don't even have that number to look up. Negative 3. It only goes to 4, so it's less than that. Okay. So it's approximately 0. So it's less than the alpha, therefore reject. So let's conclude. Conclusion was reject the null, H naught, and then state something is best. Conclude the drug potency is not as claimed. You can say, and it's statistically significant.